Hi, I'm Jinho Lee, a postdoc scholar working at Boston University School of Public Health. I'm so glad to meet you all, and you'll be watching this video probably because of a technical issue which could happen on my side, I guess. I'd like to appreciate your patience and understanding, and I hope there will be no issues for the Q&A session. And today I'm here to present a comprehensive study aimed at understanding the physical and chemical properties of aerosol generated from e-cigarettes. In this study, I focused on the metal in e-cigarette and observed the amount of metal in e-cigarette aerosols by modifying some factors that might affect its generation. As far as all of you know in this conference, e-cigarettes are rapidly replacing conventional cigarettes thanks to their less nuisance and convenience. So the use of e-cigarettes has increased worldwide in recent years from 2 to 3 fold. Recently, the media for nicotine deliveries are shifting fast towards e-cigarettes since it has less risk compared to traditional tobaccos, and it has been reported that e-cigarettes generate less aerosol and fewer kinds of potentially harmful chemicals than traditional tobacco. But people are still suggesting the risk of electronic cigarettes because they are not 100% safe, and consumers are still exposed to potentially harmful chemicals. And several studies reported that metals like arsenic, chromium, nickel, lead have been detected in various e-cigarettes. And mostly people are expecting or assuming the source of such metals are from the sources are e-cigarette liquids or metal parts of the delivery system devices. Metal particles have indeed been frequently found in e-cigarette aerosols, and their size vary widely from several tens of nanometers to several micrometers, as you can see on the figures. And it varies really a lot, and this variability likely stems from the diverse sources of metals and the formation of aggregates or agglomerates in which generate from the e-cigarette aerosols. But studying e-cigarette aerosols is getting more and more complicated because the e-cigarettes have continuously evolved in both structure and aerosol generation methods. So initially they had a simple design like cigarettes or vape pens, but by the third and fourth generations, they developed into devices that allows users to adjust e-liquid contents and atomizing power. But more recently, however, the trend has shifted back toward disposables or the simplest forms like first or second generation driven by its convenience. So most devices operate at the fixed generation voltage of approximately 3 to 4 volts. But in this study, we focused on the wattage because some heavy users still use third or fourth generation devices like the mod and tank e-cigarettes or pod e-cigarettes. And according to the CDC, these three or third or fourth generation e-cigarette device users make up more than 20% of the total e-cigarette user population. This is likely because these devices allow users to freely adjust the flavor and aerosol generation rate, which is a key appeal for them. So our first question is, does wattage matter? And are these users more vulnerable than the average e-cigarette smoker? So some people adjust the wattage of their ENDS devices not only to increase nicotine absorption, but as mentioned earlier, to enhance the flavor of the e-liquid. Because if you inhale the more vape, from the e-cigarette, you will taste the more flavor from the e-cigarettes. And others prefer high wattage for performance-related reasons, such as producing large vapor clouds, or for the cool effect it offers. We call these people cloud chasers. And if the goal were simply to consume more nicotine using a high concentration nicotine liquid would suffice. But however, for flavor chasers or cloud chasers, increasing voltage or wattage becomes a natural choice. So as a result, these users may end up inhaling greater amounts of e-cigarette aerosols and potentially more metal particles contained within it. Our next question is, does when a large volume of e-cigarette aerosol is generated, do its chemical characteristics and associated risk act uniformly, or do they vary depending on the size of the aerosol particles? This is the this is a more important question than it might initially seem. In general, most researchers studying metals in e-cigarettes tends to analyze the e-liquid itself or collect and analyze the generated aerosol without separating it by particle size. But the problem with such approaches is that they can't distinguish between the effects arising from the aerosol generation mechanism itself and differences related to the particle size. This distinction matters because in reality, when these airborne particles are inhaled and deposited in the lungs, smaller particles tend to penetrate deeper into the respiratory tract and potentially causing greater health impact even at the same concentration. To address this, our study uses a cascade impactor capable of collecting and analyzing e-cigarette particles across a wide size range from 56 nanometers to 18 micrometers, and these allowed us to determine whether particles of different sizes exhibit different chemical characteristics. With this measurement range, we believe we can capture the vast majority of e-cigarette aerosols. So as you can see, previous studies have shown that most e-cigarette aerosol particles fall well within the size range covered by the sampler we used because as mentioned before, the sampler covers particles from 56 nanometer to 18 micrometers. So to summarize, this study examined 11 aerosol size fractions and 4 levels of atomizing power. And to ensure representativeness, we selected 6 of the most widely sold e-cigarette liquid flavors on the market for testing. And we used a stainless steel chamber to generate and sample e-cigarette aerosols to better reflect the vaping topology of heavy smokers or so-called cloud chasers. We used a pulp volume of 100 milliliter, which is somewhat larger than a typical 55 milliliter vape inhalation volume. The collected particles were first weighed to determine the mass distribution across different aerosol sizes. Next, we analyzed the samples using ICP mass to measure metal concentrations. And this approach allowed us to assess whether specific metals were uniformly distributed across particle sizes or if their concentrations vary depending on aerosol diameters. So these are the results. And as expected, we observed that the aerosol generation increased with higher atomizing power. This is aligns well with the previous studies about the association between the uh, atomizing power and the aerosol generation amount. In the graph shown, the x-axis represents the wattage setting of the e-cigarette, while the y-axis indicates the mass of aerosol produced per puff. As you can see, higher wattage settings led to a clear increase in aerosol output. You can see the concentration amount of aerosol generated increases by increasing wattage of the devices. But unlikely, flavor did not appear to have impact on the mass of the aerosol produced per puff. That said, these observations should be interpreted with caution as flavoring compounds make up only a very small portion of the e-liquid by volume. In contrast, the ratio of main base components such as propylene glycol and vegetable glycerin is likely to have a greater influence on aerosol productions. Since the products used in this experiment had overall similar PG-VG composition ratios, the limited effect of flavor on aerosol mass is not surprising. So, does atomizing power or flavor affect the size distribution of the aerosol? I, and the answer from our study appears to be no. As shown in the contour plot, we plotted aerosol size on the x-axis and atomizing power on the y-axis for each flavor. The results indicate that the size distribution of the e-cigarette aerosol remains relatively consistent around in the size range of 0.56 micrometer to 1 micrometer, uh, regardless of the flavor. And this suggests that while increasing voltage does generate more aerosol, it does not significantly modify its physical characteristics like size distribution of the aerosol, and at least within the 5 to 20 watt range tested, like we did. The most interesting finding is that while increasing atomizing power from 5 to 20 watts led to more aerosol being generated, the amount of metal uh, in the aerosol did not increase. In our study, zinc and chromium were the most frequently detected metals, but their mass remained unchanged. Like you see, it shows no significant difference for in zinc and chromium, even though you increase the wattage from 5 to 20 watts. Uh, this indicates that the metal emissions from e-cigarettes do not scale proportionally with the amount of aerosol produced. Although the presence of metal particles generally follow the overall size distribution of the aerosol mass, their total mass of metal did not increase with higher atomizing power. So you can see the size distribution and the generated mass does not really changes even though you increase the atomizing power, which is really interesting. So when we bring all the results together, we can visualize them in the following graph. The gray bars represent the mass of aerosol produced per puff, and the white bars show the mass of metals per puff, and the red triangles with the dashed line indicate the ratio of metal mass to aerosol mass. As you can see, this metal per aerosol ratio does not remain constant as one might typically assume. Instead, it shows a U-shaped curve indicating that the relationship between aerosol quantity and metal content is not proportional, and it's in other words, the metals present in the aerosol not solely originating from the e-liquid because it's not proportional to the mass of the e-liquid. Given that e-cigarette devices contain metal components such as heating coils, electrodes, and other hardwares, it's likely that these contribute to the overall metal emissions during vaping. This suggests that calculating exposure or health risk based solely on total aerosol mass or metal concentration in the liquid acquired from the liquid or total aerosols may not provide an accurate assessment. If we use our data to calculate the average metal to aerosol mass ratio, like many previous studies have done, we get the blue straight line dashed line at the bottom of the graph. This is the conventional previous study approach, and you can see this approach significantly underestimates the actual matter exposure across different vaping conditions. And this does not represent the size of specific characteristics of metal concentration in e-cigarette aerosols. So to conclude, what happens as we increase the atomizing power within the 5 to 20 watts range? First, we see that the aerosol mass clearly increases, which is expected since more power generates more vapor. But interestingly, the mass of metals in the aerosol does not increase. Uh, Despite producing more aerosol, the amount of metal stays about the same. This suggests that metal emissions are not simply a function of how much aerosol is generated, and it also highlights the importance of looking beyond just total aerosol output when assessing exposure risk. Another key conclusion is metal concentration varies depending on the size of the e-cigarette aerosols. This means that simply analyzing the cumulative aerosol or the liquid itself may overlook important differences. In fact, relying only on total aerosol or liquid analysis could significantly underestimate actual metal inhalation from e-cigarette use, and this reinforces the importance of considering particle size distribution when assessing exposure risk. So, to accurately assess the health risk of e-cigarette use, we need to move beyond the bulk measurements or total aerosol measurement and account for the size-specific behavior of metal particles. And these are the sponsors for the project. And thank you for listening.